All right, hi everyone, and welcome back. Today, I want to wrap up chapters 5 and 6, which is about forces, introduction to Newton's laws, and motion in 1D. And so that's chapters 5 and 6. What's coming up is chapters 7 and 8, which is chapter 7 is devoted to Newton's third law, and chapter 8 is motion on the plane, dynamics motion in 2 and maybe even 3 dimensions. So I want to wrap this up, and there's only one small topic that I didn't talk about, which was Newton's law of universal gravitation. I will mention that because there is a problem that I gave in the homework for it, and I'm doing an example on it too. Okay, so let's look at the first problem here. So it says here, the figure shows the acceleration versus force for two objects by rubber bands, and then it says find the ratio of the two masses. So what happens is the force is given in terms of the number of rubber bands. So let's say I tie a mass to one rubber band, I extend the rubber band, and then I let the mass go, it will accelerate. So one rubber band will give you an acceleration of this much, this kind of acceleration. So for example, if you apply 5 rubber bands, you will get 4 times this unit of acceleration. Let's say that 1 unit of acceleration, whatever it is, let's say it's 1 meter per second squared. So if you apply 5 rubber bands to mass 2, it will give you an acceleration of 4a. Let's say 4 meters per second squared. 5 rubber bands will give you an acceleration of 4. How about for this one? This one, mass 1 follows this kind of graph. So it says, for example, we look where the two intersect. So 3 rubber bands will give you an acceleration of 5a. So 3 rubber bands will give you an acceleration of 5. So less rubber bands gave you more acceleration. So you conclude that mass 1 is lighter than mass 2, because for mass 2, to cause it to accelerate at an acceleration of 5a, you have to apply like 6 rubber bands, maybe slightly more, a little more than 6 rubber bands. So we conclude that mass 2 is heavier than mass 1. But let's see here. I know that, let's calculate mass 1 first, right? Mass 1. We know that F equal to ma, so the mass will be the force over the acceleration. F equal to ma, so the mass will be F over a. So mass 1, I will use here 3. So for m1, I'll write it here. m1 will be the force on mass 1 divided by the acceleration on mass 1. And for the force, I can use any place. I will just choose, because the mass will be constant. The ratio of force to acceleration is the mass. So if I use the 3 here, because it nicely intersects, these two lines intersect. Because if I use 2, I mean, it's not clear where it falls, but this one, the graph says 3. At 3, the acceleration is 5a1. So when the force is 3, you get 3 rubber bands, you get an acceleration of 5a1. And mass 2 will be, again, the force divided by the acceleration that mass 2 experiences. Mass 2 follows this line. So if you apply a force of, again, why didn't we apply 3? Because 3 doesn't intersect one of the nice squares here. By the way, this comes from chapter 5, and it's number 8, if you want to have a nicer, look at a nicer figure than the one I drew here. So at 5, you get an acceleration of 4a1. So 5 gives you 4a1. So if you combine these, if they want the ratio of m1 over m2, so just combine them and divide. So m1 over m2 will be this divided by this. And when you divide two fractions, it's like multiplying by the reciprocal. So you get the first fraction, 3 over 5a1. And then you multiply by the reciprocal of this one, which is 4a1 over 5. 4a1 over 5. And you get what? The a1's cancel. And 3 times 4 is 12, and 5 times 5 is 25. And so the conclusion is m1 over m2 is 12 over 25, meaning m1 is slightly less than half of m2, because 12 over 25 is slightly less than 0.5, right? So anyways, that's the ratio, all right? So let's look at the next one here. For here, it says the figure shows the acceleration of objects of different mass that experience the same force. So you apply the same force to different objects. So let's say the first object is 100 grams. You apply a certain force to it, and it gives you an acceleration of 15 meters per second squared. If you apply that same force to 200 grams, you get an acceleration of about, well, somewhere between 5 and 10, somewhere here, maybe 8. If you apply the same force to 300 grams, the acceleration is 5. And so the question is, what is the magnitude of the force? Well, we know that the force is, the net force on an object is the mass of the object times the acceleration of the object. So we're free to choose to calculate the force anywhere we like. And so we choose where the x and y axes, they have clear coordinates here. So for example, this point has the coordinates of 100 grams and 15 meters per second squared. So let's calculate that. So I can use that F equal to ma. And so if I use the 100 grams, which is 0.1 kilograms, make sure you use kilograms. And then the acceleration is 15. And 0.1 times 15 would give me 1.5 newtons. 1.5. So the force applied is 1.5 newtons. If you would like to double check your work, you can calculate the force using this. So you can use the other point. So F equal to ma again. Right. So that mass over there is 300 grams or 0.3. The acceleration is 5. And 0.3 times 5 is also 1.5. So the applied force, we conclude, is 1.5 newtons. Okay. And all right, let's continue. We'll go to, this is chapter 5. So let's go to chapter 6 now, where we start applying Newton's second law. All right. So it says here, the first question here says, the position of a 2 kilogram mass is given by x equals to 2t cubed minus 3t squared. T is in seconds and x will be in meters. Here the 2 and the 3 in front of the t cubed and t squared, they have appropriate units so that you end up with a position in meters, and the time, of course, is given in seconds. Everything is in the SI units. And so this is the position, and they say, what's the net force on the mass at time t equal to 0 and at time t equal to 1 second? So how are we going to do that? Well, I know that the net force on an object, will be the mass times the acceleration of the object. So I know the mass of the object, it's 2 kilograms, but what's the acceleration? Oh, the acceleration, I have the position, so I just have to take the derivative once to get velocity, and then take the derivative again to get the acceleration. So let's see. So v is dx dt. And so let's take the derivative of this with respect to time. You take the derivative here, the 3 comes down, so you get 6 t squared, and then minus 6t for this one. And then we will get the acceleration. So the acceleration will be dv dt. Take the derivative, so the 2 comes down, so you get 12t, and then here you get minus 6. Okay, so that's that. And therefore, the force here will be 2 times the acceleration, because the mass is 2. So we can just go here and multiply this by 2. So the force will be 2 times the acceleration. So 2 times 12t, that's 24t, minus 2 times 6 is 12. So that's the force at any time. So for part A, the force at time t equal to 0 seconds, you plug in 0 seconds here, so the force will be, what, 24 times 0 minus 12, and that's minus 12 newtons. So if you're moving along the x direction, this is the x direction, so it means the force originally was to the left. Okay. And then for part B, what's the force at t equal to 1 second? Well, the force at 1 second will be 24 times 1 times 1 minus 12. And so we have 24 times 1 is 24, minus 12 is 12, so that's positive 12 newtons. Okay, so the force is actually time varying. It's not a constant force. It's changing. Okay. Very good. And so now for this next problem, here is what I wanted to talk about. They say you got the sun and the earth. Earth is orbiting around the sun. So here is the sun, here is earth, and earth is going around in a certain orbit. It happens to be elliptical. Doesn't matter. So why does the earth not go in a straight line? Because, I mean, it's going around in an ellipse. Why doesn't it go in a straight line? Because we know Newton's first law says if the net force on an object is equal to 0, that object will just continue going along a straight line with constant speed. So clearly, if it's bending, there is a net force on it. Where does the net force come from? It comes from the gravitational pull of the sun onto the earth. So here is the sun, here's the earth. The same way when you're on the surface of the earth pulls you down, and it pulls me down, and it pulls everything down. The earth itself is being pulled by the sun, and by we didn't talk about Newton's third law yet, but by Newton's third law, the earth is also pulling on the sun. So if you're interested in the earth, then you look at the forces on the earth itself. And then if you're interested in the sun, then you consider the forces on the sun. And here we're asked about the force on earth. The gravitational force on earth due to the sun, the gravitational force is always pulling. So the sun pulls the earth toward itself. It's always along the line that connects the two objects. So let me go to the next board here and then come back to this one. So just in general, Newton's law of gravitation, it says if you have any two masses, regardless, they are big, they are small, if you have any two masses, so let's say you have M1 here, let me draw it bigger. So here is, let's say M1, sorry, I'm going to put the M1 here, and I'm going to put, this is the center here. Let's say it's uniform density, uniformly distributed, like what we say, isotropic, basically. The density doesn't change with the angle. And let's say here is another mass, M2, and the distance from center to center is r here. We will talk about the vector form of this because force is a vector. The separation between M1 and M2, usually we call it R12, the distance from 1 and 2. But since we have just two masses, just call it R. Then we know that Newton has three laws of motion. Newton's first law, Newton's second law, Newton's third law. Newton also, and those laws, they say F equal to ma or whatever for the second law, for example. Newton's law of gravitation tells you what the force is. So we know that the force on an object is equal to the mass times the acceleration of that object. Your job is to find the force and then use that force to calculate the acceleration. In this case, and Newton's second law works all the time. Well, when the objects are large enough and not moving at the speed of light. Or close to the speed of light, I should say. So what is the force in this case? I mean, there is no string connecting the objects, there is no spring, there is no normal force, there is only the force of gravity. And the question is, how much is it? The force of gravity on Earth is mg, and g is about 9.8 downward. But this is not that force, because we're not on Earth. In fact, it's the Earth that's being pulled. Newton says that force, the force between them, is equal to the product of the two masses, the first mass times the second mass, divided by the distance between them squared. And then to make the units correct, there is a universal constant here, this capital G. And G is 6.67 approximately. There are more, if you want to be more accurate, you can look it up. I think there are two more. 6.67 times 10 to the minus 11. And the units are, well, the left-hand side has to be newtons. I have meters squared on the bottom, so I need meters squared on top. I have kilogram times kilogram on the top, so I need to cancel them to get kilograms square, so I need kilograms squared on the bottom to cancel them. And then I need to end up with newtons, so there is a newton here. So those are the units of g. And it's always this number, it's constant. See, the acceleration due to gravity, that 9.8, varies with height. But this number here is universally constant. It's a constant. Okay? So for instance, I said between any two objects, so if you take a 1 kilogram object, so let's say I have two, a 1 kilogram here and a 1 kilogram and a 1 kilogram object, 1 kilogram. So this says any two things will attract each other. So these two erasers, they're not 1 kilogram, but they have a certain mass. So the question is, why are they not just moving and colliding with each other? Sorry, Chuck. Why are they not just moving and colliding with each other? Well, the answer is, let's say they are 1 meter apart. 1 meter apart. Then the force between them, in this case, the force would be G, 6.67, times 10 to the minus 11. Let's say each mass is 1 kilogram, and the other mass is 1 kilogram, right? M1 times M2, divided by the distance between them squared. Let's say the distance is this big, about a meter, so 1 squared. So the force would be 6.67 times 10 to the minus 11. So this is undetectable, tiny, very small. Undetectable under normal circumstances. So that's why they're not going to move. So they are being attracted with each other, but they can't move. Why? Because there are other forces. There is air resistance, there is the force of friction, mainly. And that force of friction simply does not allow them to, it's much larger than this force. It cannot, so this force basically is totally insignificant. However, when the mass is not a kilogram, when the mass is like the mass of the Earth, 10 to the 24 kilograms, or the mass of the Sun, which is I think 10 to the 30th kilograms, approximately, then this becomes significant, and that force would be large. So let me do one more example. Let's say you're here. Here's Earth. Here's Earth. This is Earth. This is M1, mass of the Earth. M1 is the mass of the Earth. And you're here. You're the person here on the surface of the Earth. You are M2. Okay? And so the force on you due to the Earth, you're here. It says the force on you will be your mass. Your mass is M2 times the mass of the Earth, which is M1, divided by the separation between you squared times G. Okay, times G. And so the force on you due to the Earth would be G. Again, your mass is M2. This is the mass of the Earth. M1 is the mass of the Earth, divided by the separation between you squared. The separation between you is the distance from here to here. It's basically the radius of the Earth, and the radius of the Earth is 6.37 times 10 to the 6. 37 times 10 to the 6. Okay. I need to square it. R squared. So that's the force on you. And Newton's second law says the net force on you will equal to your mass times acceleration, would be the mass times acceleration. Your mass, so that's M2. And so let's say you're like this pan, or you're slightly above like the surface of the Earth, and you let go. So the only force on you is the force of the Earth. Once you hit the Earth, there is the normal force. But I want to know what just the acceleration due to the force of the Earth by itself will be. What would it be? Well, let's calculate the acceleration. So I have this. So your mass simply cancels. And so your acceleration will be G, the mass of the Earth, over this number squared. G is 6.67 times 10 to the minus 11. Mass of the Earth is 5.98 times 10 to the 24 divided by 6.37 times 10 to the 6, but don't forget to square this. Excuse me. My question to you, before you even plug in the numbers, what do you think this number would be? You're on Earth. Here's a pan on Earth. The Earth pulls it down and it accelerates. With what acceleration would it go? Well, you should not be surprised when this would be about 9.8 meters. per second squared. So it should be the acceleration due to gravity, and it comes out like that. Okay, very good. So now I'm going to use this formula and go back to the previous problem. We will talk about that more, I think in chapter 12 or 13, I forget. 8, 9, 11. Yeah, approximately, maybe 13, I think chapter 13. So they say the Earth is 1.5 times 10 to the 11. So R, the separation, R is this number here, 1.5 times 10 to the 11 meters. That's large. And then the Earth's mass is this, and the Sun's mass is that, 1.99 times 10 to the 30th. What's the acceleration of Earth toward the Sun? So the Earth will be moving toward the Sun. By the way, the Earth is not, it will accelerate toward the Sun, but it doesn't collide with the Sun, because Earth will have it has a velocity this way. So by the time it has accelerated toward the Sun here, the Earth is there, because you still have a velocity this way. So by the time you have moved here, you're now located here. And then once you're there, you still have a tangential velocity. So by the time you accelerated toward the Sun, you're actually here now, because so you move this way, but you still move the other way, so you're here. So you're not going to just collide, because you have some tangential velocity. Yes, if you start at rest, you will just go and collide with the Sun. But you're not at rest. You still have a tangential velocity. So what's the acceleration? So I know that the force on Earth, the net force due to Newton's law, was the net force on an object will equal to the mass of the object times the acceleration of that object. The force on the object here, we're talking about the Earth, so it would be G. The force on it is due to the Sun, so it's G. The mass of the Sun times the mass of the Earth divided by the separation between them squared, and that should equal to the mass times acceleration. We're talking about Earth, so it's the mass of Earth times the acceleration of Earth. The mass of Earth simply cancels, and the acceleration will just be this. The acceleration will be G at 6.67 times 10 to the minus 11. The mass of the Sun is 1.99 times 10 to the 30th. 1.99 times 10 to the 30th. That's the mass of the Sun divided by R squared. And R is, what's R? 1.5 times 10 to the 11. 1.5 times 10 to the 11. And I have to square it. And I will just quote you the number here. I happen to have it. It is 5.9 times 10 to the minus 3. Let me make sure I got it. Yeah, 5.90 times 10 to the minus 3 meters per second squared. And yes, all right, good. I think I have it right. 1.0. Yes, good. Right, so it's a smaller, it's not like 10 to the, I'm sorry, it's not like 9.8. It's 5.9 times 10 to the negative 3. Again, we will come back to this in the future. We will now look at a different problem, and so I will, so let's look at it. All right, so we're still in chapter 6. So it says here, Bob is pulling a 30-kilogram filing cabinet. It's like a cabinet, and with a force of 200 newtons, but the filing cabinet refuses to move. So the cabinet just refuses to move. And it says the coefficient of static friction between the cabinet and the floor is 0.8. And what is the magnitude of the force of friction on the filing cabinet? So let's draw something. So here's the floor, here's the filing cabinet, here's Bob. Bob is here, and Bob is, I'll draw Bob. I would just say Bob applies a force this way, trying to pull it, and 200 newtons. applying a force of pull of 200 newtons. What are the forces on the cabinet? Well, there is Bob's pulling force. There is mg, the mass of the cabinet, right? The weight of the cabinet, the pull of the earth on it, mass times gravity. Of course, there is the normal force. And is this the full picture? The answer is no, because if this were the full picture, along this vertical direction there is no motion, fine, because these two forces cancel. But horizontally, there will be a net force and it should accelerate. There is no question about that. Newton's second law says if there is a net force on you, you should accelerate. So we conclude it's not accelerating, so there is another force opposing that. It wants to oppose the relative motion between the two objects, and that's the force of static friction. And the question is, what's the force of static friction on the object? So let me show you something, let me tell you what the answer is. Since the cabinet is not moving, the net force on it is equal to 0, and that means in the y direction, the normal force is simply equal to mg in this direction. In the x direction, let me call it, here is my positive x, and this is my positive y, those are my coordinates. In the x direction, I have 200 newtons to the right, and a force of friction to the left, so 200 minus the force of friction, because it's to the left, that equals to 0, and so the force of static friction is simply 200. That's the answer, it's just 200 newtons, it's as simple as that, 200 newtons. You might say, well, the force of static friction is actually mu s times the normal force. And the answer is no. The force of static friction, if you remember, it takes values between 0 and some maximum value, and that maximum value is mu s times the normal force. Mu s times the normal force. So, the force of friction, in this case, it's 200 newtons. And it can be as large as the force of static friction. The maximum value will be mu s times the normal force. Mu s is 0.8, and the normal force is mg. The filing cabinet is 30 kilograms times 9.8. So the force of static friction will be, let me check it out. So you might be inclined to say it's 0.8 times 30 times 9.8. So that's 235.2, 235.2 newtons. What this means is, see, if Bob doesn't apply a force at all, the filing cabinet will just sit there, and then the frictional force will simply be 0. If there is no force this way, there will be no friction the other way. You apply 1 Newton this way, the force of friction can keep up with it. It will apply 1 Newton, because it can go anywhere from 0 all the way to 235.2. You apply 100 newtons, friction will happily oppose you, will apply 100 newtons. You apply 200, it will happily apply that. You apply 235 newtons, the force of friction will be 235 newtons. You apply 231.2 newtons, you're about to move. You apply 235.21 newtons, then you will start moving. You will break out from the static friction, and then you start sliding, and once you start doing that, it is kinetic friction then. It's not static friction. Okay? I hope that's clear. Force of static friction does not take only one value. It takes a range of values between 0 all the way to some maximum value. You should calculate that maximum value and then ask, is the force that I'm applying, is it exceeding that value? If it is, then yes, you will be moving, and then you will be sliding, and that's kinetic friction. If you didn't exceed it, then you're still at rest, and the force is still static friction. You're not, I'm sorry, I shouldn't say at rest, because we'll have rolling. There is no relative motion between the two surfaces. Come back to that point when we do rolling. Okay. So now let me pause this, and we'll go to the next video where we talk about problem 638. All right, welcome back. And we're looking at problem number 6.38. Oh, I'm sorry. I should be going to a different video. Sorry. I will come back in another video.